Hello, welcome to a new video of differential equations. As I mentioned on a previous video where we were talking about the green function, today we are going to solve this particular differential equation that I have here with the method of the green function. So first we need to construct that green function. Okay, so first of all, here we have that the second derivative with respect to x of u plus k squared u is equal to f of x. Okay, and as we mentioned, we can identify this differential equation as a linear differential operator applied to the function u equals to the function f of x. Okay, where in this case, of course, L is going to be the operator, the second derivative with respect to x plus k squared. Okay, perfect. And we need to take into account that the conditions that define this problem are these, that are that x goes from 0 to L, and the boundary conditions that tells us that u of 0 is equal to u of L, and this is equal to 0. Okay, so we can immediately identify that this differential equation has the structure of a harmonic oscillator, right? And well, in this case, we know that we can propose a solution for that of the form u of x equals to a of x times cosine of kx plus b of x times sine kx, like this. Okay, and what we are going to do is to use the method of variation of parameters to find two equations that will allow us to find what are these a of x and b of x. So what we are going to do first is to take this into the differential equation. So first we are going to calculate the first derivative of u, and this is going to be, well, a prime cosine of kx, and then minus a k sine of kx, and then plus b prime sine of kx, and then plus bk cosine of kx. Okay, so after finding the first derivative, we know that in the method of variation of parameters, we take at this step this term and this term to be equal to 0. Well, the sum of them, right? So we are going to get that a prime cosine of kx plus b prime sine of kx is equal to 0. This step is made to make the process simpler. Okay, so this will make the calculations to be easier, but we need to save this equation because we are going to use it later. Okay, so if we take this to be true, then the first derivative of u is going to be minus ak sine of kx, and then plus bk cosine of kx. Okay, so with this, we are able to find the second derivative of u, which is going to be minus a prime k sine of kx, and then minus, it will be a k squared cosine of kx, then plus b prime k cosine of kx, and then minus bk squared sine of kx. Okay, so we are going to bring this equation to the differential equation that we have initially, and if we substitute that, we are going to get all this expression. Let me copy, and then a plus k squared times u, but u is a cosine of kx, and then plus b sine of kx, and this is equal to f. Okay, perfect. So from here, we can notice that this element will be cancelled with this element, and this element will be cancelled with this element. So from here, we can get that minus a prime k sine of kx plus b prime k cosine of kx is equal to f of x. Okay, perfect. So with this, we have a second equation that will allow us to find a prime and b prime. Okay, so I'm going to construct the system of equations that we need to solve to find a and b. So how would it be? We will have here cosine of kx, then here sine of kx, then this element will be minus k sine of kx, and this k cosine of kx. This will multiply a vector that is a prime, b prime, and this is going to be equal to 0 and f of x here. Perfect. So I'm going to use the method of the inverse of the matrix to find the solution to this system of equations. Okay, so we know that if we set this matrix to be equal to M and this to be equal to a vector X and then this to be equal to maybe a vector Y, we have that M times X is equal to Y, and we want to find X. So this will be that X is equal to M inverse times Y. Okay, perfect. So we need to find M inverse. So what is that going to be? Well, we know that looking at is a second, a 2 by 2 matrix, it is very easy to find the inverse, right? We will have that M minus 1 is going to be equal to 1 over the determinant of the matrix, which is going to be K times, K cosine times cosine, which is K cosine squared. And then minus times this minus, we will get a plus. K times sine. Okay, so that will be something like this: k times cosine squared plus sine squared, but we know that this is equal to 1, so the determinant is just going to be k, like this. Okay, perfect. And then we know that, if we want to find the inverse of a 2 by 2 matrix, we just need to switch this element with this element and then multiply by a minus sign this element and this element, right? Okay, so if we do that, we are going to get here that we have k cosine of kx, and then here cosine of kx, then this will be minus sine of kx, and this k sine of kx. Okay, perfect. So with this, we can say that a prime b prime is equal to m inverse times 0f, which is 1 divided by k times, this matrix. And then this multiplies 0f. Perfect. So from here, we see that a prime is going to be 1 over k times this times 0 is 0, and then minus sine f. So it will be minus f sine of kx divided by k, and b prime is equal to, it will be f cosine of kx divided by k. So from here we can say that a is equal to minus the integral from an initial value a that we will find later to the value x of, let's say, f of y sine of ky divided by k dy, and b is equal to the integral from an initial value b to x of f of y cosine of ky divided by k. Okay, perfect. Like I said, these values correspond to the element of the integral that is a constant, right? So with this, we can now construct the solution u of x that we proposed. So we had that u of x was equal to a times the cosine, right? So we will have here cosine of kx divided by k for this k, a minus here, and then the integral from a to x of f of y sine of ky dy, and then plus b times the sine, right? So we will have here sine of kx divided by k, the integral from b to x of f of y cosine of ky dy. And I forgot dy here. Okay, perfect. So this will be like the whole solution u of x. but we now need to find what are the values of a and b. So here's where we are going to remember the initial conditions or the boundary conditions that says that u of 0 is equal to 0. So we are going to take the value x to be equal to 0, and this whole thing is going to be 0 equals to, here we will have cosine of 0, and the integral from a to 0. And here we will have the sine of 0, which is going to make this whole element to be cancelled. So we will have minus cosine of 0, which is 1, divided by k, the integral from a to 0 of f of y sine of ky dy. And notice something interesting here. We have an integral that needs to be equal to 0, and, well, it is an integral of an arbitrary function f of y. So in general, we can consider that this integral is for, well, it has the limits of integration to be equal, right? Because we know that when we have the same limits of integration, we get 0. In this way, it doesn't matter what function do we have here inside. And looking that we do not know the form of f of y, we do not have other option to consider that a needs to be equal to 0 for this to be 0 all the time. Okay, so this is telling us that a is equal to 0. Perfect. So now we are going to make use of the second boundary condition, which is that u of L is equal to 0, right? So what is this going to be? Well, we will have here that 0 is going to be minus cosine of k times L divided by k, the integral from 0, which is a, right, to x of f of y sine of ky dy, and then plus sine of kl divided by k, the integral from b to x of f of y cosine of ky dy. And I forgot to substitute the value of x here, which is L, right? Okay, so from here we can say that this thing is equal to this thing just with the plus sign. So let me erase this 0, take a plus here, and then set these to be equal. And again, I forgot to substitute the value of x here in the limit. Okay, so here we are going to make use of a trigonometric substitution that is very famous. We are going to make use of the next. We know that the sine of k times y minus L can be seen as a sine of ky cosine of kl minus sine of kl and then cosine of ky. Okay, notice that here in this integral we have cosine kl and sine ky, which is this element over here. So we are interested in that. So we will have that sine of ky cosine of kl is equal to sine of k times y minus l plus sine of kl cosine ky. So we are going to substitute that in our integral. So we will get 1 divided by k, the integral from 0 to L of f of y, and then all this thing, sine of ky minus L plus sine kl cosine ky dy. And this is equal to sine of kl divided by k, the integral from b to L of f of y cosine of ky dy. Now, notice that this element is actually the same element that we have here in this expression. So we are going to be interested in combining these elements in just a single integral. So we are going to get 1 divided by k, the integral from 0 to L of f of y, sine of k times y minus L dy, and then plus 1 divided by k, the integral from 0 to L f of y, sine KL cosine ky dy, and this is equal to the integral from b to l of f of y cosine ky sine kl dy. So notice that in this integral we can switch the order of the limits of integration just by taking a minus sign here. We take the b here, the l here, and then we can say that 1 divided by k, the integral from 0 to l of f of y sine of k times y minus l dy is equal to, and let me recall that there is a k dividing here, right? Okay, so this will be, we will have a minus here, a 1 divided by k here as a common factor, and then looking at we have the sum of an integral from 0 to L and then the integral from L to B, we can combine that integral to be an integral from 0 to B, right? Because recall the integral from 0 to L plus the integral from L to B is the integral from 0 to B. So that is what we are doing here. We are combining both integrals to get that, well, the same argument inside, which is f of y sine kl cosine ky dy. Okay, perfect. So we are going to save this result because it will help us to be able to erase the b in the expression for u. Okay, so just let me bring back what we had found for u of x. Okay, and this was the expression that we found for u. Recall that I have already substituted the value of a. So from here, we have that u of x is equal to minus 1 divided by k, the integral from 0 to x of f of y. And I'm going to make use of the trigonometric identity again here to see that this is equal to sine of k times y minus x, and then plus sine of kx cosine of ky. dy here plus sine of kx divided by k, the integral from b to x of f of y cosine of ky dy. Okay, so I'm going to split this integral into two pieces, and then I'm going to make a switch of limits of integration here just by taking a minus sign. So if we do that, we are going to get that u of x is equal to minus 1 divided by k, the integral from 0 to x, f of y, sine of k times y minus x, and dy, minus 1 divided by k, the integral from 0 to x of f of y, sine kx cosine ky dy, and then minus sine kx divided by k, the integral from x to b of f of y cosine of ky dy. Perfect. Notice that after making this switch of limits of integration, we have again an integral from 0 to x plus an integral from x to b. So this will be an integral from 0 to b. Of course, we have the same argument in both integrals, right? We have f of y sine kx cosine ky, and the same thing here. So we can do that without any problem. And this is going to take us to u of x equals minus 1 divided by k, the integral from 0 to x, f of y sine of k times y minus x dy, and then minus 1 divided by k, the integral from 0 to b of f of y sine kx cosine ky dy. Okay, but recall that we had found an expression for the integral from 0 to b of this thing over here. Recall that we have here the integral from 0 to b of f of y and cosine of ky, right? This sine of kl is not too much important because we have here the integral from 0 to b of f of y cosine ky, but we have a sine kx here. but in terms of the integral, it's just a constant. So we are going to make use of this result here. So first, let me rewrite this. We will have u of x is equal to minus 1 divided by k, the integral from 0 to x, f of y sine of k times y minus x dy. And then we will have here minus, or actually plus, sine kx that will multiply minus 1 divided by k, the integral from 0 to b of f of y cosine of ky dy. Right? With this, we can see more clear that this thing is what we have here. Okay, just by taking this sine kl out. Yeah, if we do that, if we take that sine kl out, let me erase it, and it will be here, right? It will be k sine kl. Okay, so that integral that we have here is going to be equal to this. So we substitute that result to get that u of x is equal to minus 1 divided by k, the integral from 0 to x of f of y sine k times y minus x dy plus sine kx and times this result here. So it will be k sine kl here dividing, and then the integral from 0 to l times f of y sine of k times y minus l dy. Perfect. And notice that this u of x no longer has dependence on a and b. So we have eliminated those variables. Okay, so what we are going to do now is to split this integral into two, one from 0 to x and the other one from x to l. We are going to get that u of x is equal to minus 1 divided by k, the integral from 0 to x, f of y sine of k times y minus x dy, and then plus sine kx divided by k sine kl, the integral from 0 to x of f of y sine k y minus l dy, and then plus the integral, well, actually sine kx k sine kl, integral from x to l of f of y sine of k y minus l dy. And looking that we have the integral from 0 to x in this element and in this element, we are going to combine in just one integral. So what are we going to get? We will have that u of x is equal to 1 divided by k, the integral from 0 to x of f of y that will multiply, it will be sine kx divided by sine kl times sine ky minus l, and then minus sine k times y minus x, and then dy. And then plus sine kx divided by k sine kl, the integral from x to l of f of y sine k times y minus l dy. Okay, perfect. So we are going to notice this element that we have here. We can see that this can be seen as a sine kx sine ky minus l minus sine ky minus x times sine kl, all divided by sine kl. Okay, so we can immediately notice that this element that we have here and this element that we have here, well, they can be split by the trigonometric identity that we have been using all the video. So this is sine kx times sine ky cosine kl minus sine kl cosine ky, and then we will have here minus sine kl that will multiply sine ky cosine kx minus sine kx cosine ky, and all divided by sine kl. Okay, perfect. So obviously some terms are going to cancel, and those terms are this and this, right? We have sine kl, sine kx, cosine ky plus, and then we have minus sine kl, cosine ky, sine kx. Okay, so at the end we will get sine kx, sine ky, cosine kl minus sine kl, sine ky, cosine kx divided by sine kl. And again, using the same property but at the inverse, and taking a common factor sine ky, we will have that this multiplies sine of k times x minus l and divided by sine kl. Okay, perfect. So we are going to bring back this result to our function u of x to see that this is 1 divided by k, the integral from 0 to x of f of y, that multiplies sine ky divided by sine kl, sine k x minus l dy plus sine kx divided by k sine kl times the integral from x to l of f of y sine k y minus l dy. So I do not know very much why the book where I take this information from takes a minus sign out of the sign and switch the order of the x and the l. But just to respect the book, we are going to write it in that way. So this will be minus 1 divided by k, the integral from 0 to x of f of y sine ky sine kl times sine k l minus x dy, and then minus sine kx divided by k sine kl, the integral from x to l of f of y sine k of l minus y dy. Recall that sine of minus x is equal to minus sine x because the sine is an odd function, right? Okay. And what we can notice here is that, again, we have an integral from 0 to x and then an integral from x to l. So we would like to have kind of like a function that will allow us to write the function u of x in terms of just one integral. So we can propose that function to be maybe something like this. It will be the integral, of course, from 0 to l of this f of y, which is a common factor, times that function, which is going to be, of course, of two variables, right? Because here inside the integral, we have the variable y, we have the variable x. So this is telling us that that function that we need to propose has to be of the variables x and y, okay? And then, of course, this is an integral over y. Perfect. So with this, we can define a function that it is valid from the interval from 0 to l, of course, okay? But, well, it is, we have here an integral of y, okay? So this value of y is going to be changing in the interval 0, l, right? Actually, this interval goes from 0 to l, and it passes by the x. So here we have these different values of y, and here we have different values of y again. So what this is telling us is that this function is going to be equal to these elements that we have here when we take the integral from 0 to x. So when we are in this part of the interval. Okay, so g is going to be this thing over here when we are from 0 to x. And then if we go from x to L, this function g will take the value sine kx divided by k sine kl times sine kl minus y. So with this, we can define just one integral, but we need to write that down. So it will be that g of x comma y is equal to, it will be minus sine ky divided by sine kl, and we have a k here, of course, times sine kl minus x from 0 to x. Okay? So let me write this as 0 from 0 less than or equal to y, which is less than or equal to x. And we will see why I'm writing less than or equal to x. Okay? But first, let me finish writing that from the interval x to L, we will have that g is defined as minus sine kx divided by k sine kl times sine kl minus y. This is from x to L. Perfect. So what we need to notice now is that this function g is actually continuous on the point x. If we evaluate y to be equal to x in this expression, we see that we are going to get this other expression, right? So this is telling us that g is continuous, and that is good news. Okay, so the most important idea. We showed that we are able to express the solution to the differential equation, which is u, as the integral from 0 to L. That means an integral that covers the whole interval of definition of the differential equation. And this is the integral of the function f, right? Which is, remember, the term that makes the differential equation not homogeneous, times a function of two variables, which is g. And we were able to define what is the form of g. Okay? So that is the main idea of the green function. Then if we are able to solve this integral, we are able to solve the differential equation. So this function g, of course, is known as the green function associated to the differential equation. Okay, perfect. An interesting exercise that you could do at your house maybe is to prove that the derivatives of this function g, the lateral derivatives, right? When y approaches x from the left, and then when y approaches x from the right, well, these derivatives are not equal. Okay, so that means that g is not differentiable at the point y equals x. So that's an important fact. Perfect. So I think that with this, I'm going to finish the lesson. I hope you enjoy it, and thank you so much for watching the video.